हेलो विद्यार्थी मित्रों, चैप्टर 1 में लास्ट टाइम एक्सरसाइज 1.4 कम्प्लीट करेली है। आज આપણે મિસેલેનિયસ एक्सरसाइज 1 લઈએ। मित्रों, up to this stage we already seen the definition of function, relation, types of functions, and lastly we already seen binary operations with their properties. Only these 4 concepts are there in chapter number 1. First of all, first concept is relation and types of relation: reflexive, symmetric, transitive, skew symmetric, and equivalence relation. And already seen some example based on that thing. Then we already see definition of function, types of function, one-oneness, one-to-ness, invertible function, and then example based on that. And lastly we seen that binary operations. And today we are going to see miscellaneous exercise. Let us see one by one. See here. First one. F from R to R defined by fx is equal to 10x plus c. Find function g from R to R such that f of g is equal to g of f is equal to IR. Clear? F is linear. Identity function is also linear. Definitely g is also linear. Here for f from R to R, f of x is equal to 10x plus 7. We want g. Suppose g from R to R, g of x is equal to ax plus b, ab belongs to R, a not equal to 0 is a function such that a composition of f and g is known as f of g, and composition of g with f is g of f is equal to identity function. F and g both are from R to R, so f of g, g of f and I are also from R to R. All functions from R to R. There is no need to mention whenever domain and codomain of both functions are same, then definitely their composition exists. We want g of x. Now let us use f of g is equal to IR first of all. Now for all x belongs to R, f of g at x is equal to identity at x. That is equal to f of g of x is equal to x. What is f of g of x? Ax plus b is equal to x. Now what is fx? See here, 10x plus 7, and therefore 10 of ax plus b plus 7 is equal to x. Yes or no? Yes. And therefore 10ax plus b plus 7 10b plus 7 is equal to x. So can I write here 1 into x plus 0? Yes. Now compare coefficients. 10a is equal to 1, 10b plus 7 is equal to 0. So A is equal to 1 by 10, B is equal to minus 7 by 10. And therefore it is Gx. Gx is equal to Ax plus B is equal to 1 by 10 into x minus 7 by 10 is nothing but x minus 7 by 10. Now let us see here. Next part, change the color. For all x belongs to R, g of f at x is equal to also identity function at x. So it is g of f of x. G of f of x is equal to x. What is fx? 10x plus 7 is equal to x. Now it is gx, ax plus b. A into 10x plus 7 plus b is equal to x. 10ax plus 7a plus b is equal to 1 into x plus 0. So 10a is equal to 1, 7a plus b is equal to 0. A is equal to 1 by 10, B is equal to minus 7a, minus 7 into 1 by 10, that is minus 7 by 10. So, and therefore what is Gx? 1 by 10 into x minus 7 by 10, that comes out x minus 7 by 10. So what is here? Therefore, and therefore g from R to R, g of x is equal to x minus 7 by 10 is a function for which f of g is equal to g of f is equal to IR. In other words, this is the third method to find inverse also. And therefore g of x is nothing but f inverse x, and therefore f inverse x is equal to x minus 7 by 10 also. This part is extra, we don't want to see here, but that is the extra part. Next, now see here, very important sum. See, here W is the set of whole numbers for set W of all whole numbers. F is function from W to W. F of n is nothing but n minus 1 if n is odd, n plus 1 if n is even. Then show that f is invertible and find inverse of f. Here, most important example. Now, first of all, I would like to recall the concept of inverse function once again. See, if f from A to B is 1 1 n on 2, then f is invertible. Here, that we know. And f inverse is a function from B to A. Put as a note, first note. Now let us recall how to check one-oneness. There are two ways. For all x1, x2 belongs to A, x1 not equal to x2 implies fx1 is equal to fx2. Then function is 1, 1. Or, now see, we already seen in logic, mathematical reasoning, if P implies Q, then what is contrapositive statement? Negation Q implies negation P. In our case, this one is P and this one is Q. So what is negation? Here negation. For some x1, x2 belongs to A, f of x1 is equal to f of x2. See, negation of f of x1 is equal to f of x2 is this one. Implies x1 is equal to x2. Negation of P, this is P, so its negation is this one, negation Q. So negation of this one is this thing. Then f is 1, 1. That we know. This is the second knot. Why we are recalling at last? Because of then it is easy to identify how to solve the given sum. Next we will listen how to see the onto-ness of a function. Third knot. If for f from A to B, range of f is equal to B, codomain of function f, then it is onto. Or range of f is equal to codomain means every element of codomain is associated with some and some element of domain. That means for all y belongs to B, there exists x belongs to A such that f of x is equal to y. Then f is onto. And fourth one, see, this is the first way to check out whether given function is invertible or not, as per previous sum. Second way to check the invertibility of a function f is, if f from A to B, there exists function from G from B to A such that f of G is equal to identity function on domain of G and G of f is equal to identity function on domain of f, then G is inverse. See, this is the second way to check the invertibility of a given function. Now here this method is not useful because set of whole numbers are given to us. Whenever function from n to n, z to z or any number to number is given in place of r to r or in place of q to q. If function from n to n, z to z, n to z, whatever may be. But other than r to r and q to q, then use this one-ness and onto-ness to check the whether given function is invertible or not. Clear? Yes. Now let us see here. Here f of n is equal to n minus 1 if n is odd, n plus 1 if n is even. That is given. Yes or no? Let us check it. Yes. N minus 1 if n is odd, n plus 1 if n is even. Now here we are going to check one-ness and onto-ness. Here x1, consider two whole numbers x1 and x2. Then there are three possibilities. Either they are even or they are odd, or one of them even, another one is odd. So let us see all the three possibilities. First one, you can consider x1, x2 also, or n1, n2 also. If x1 and x2 are both odd, then f of x1 is equal to f of x2 implies odd, means n1 minus 1, x1 minus 1, x2 minus 1, implies x1 is equal to x2. Third one, that is, if x1 not equal to x2, then fx1 not equal to fx2 also. Second one, if x1 and x2 are both even, then f of x1 is equal to f of x2 implies x1 plus 1 is equal to x2 plus 1. Yes or no? Yes. This implies x1 is equal to x2. 1 cancel. Third one, if x1 is odd and x2 is even, then x1 not equal to x2. Clear? And f of x1 is equal to x1 minus 1, because of if n is odd then n minus 1. N is even. Yes or no? Odd minus 1 even. Comma. F of x2 is equal to x2 plus 1. N is odd, because x2 is even. That is f of x1 not equal to f of x2. Clear? And therefore, for all x1, x2 belongs to W, means set of whole numbers, x1 not equal to x2 implies fx1 not equal to fx2. And therefore, f from W to W is 1, 1. Next, our aim is to show one-to-ness. Now, range of f is equal to f of n. N belongs to W. Or you can write f of W also. And that is equal to n minus 1 if n is odd, union n plus 1 if n is even. See. Now see, 1 is odd. So 1 minus 1 is 0. See, 0 is whole number. Whole number means in place of set of integer they are taking this thing. That means 0, 1, 2, 3, 4, 5 likewise. N union 0. So that is equal to f of W, and that is W. And therefore range of f is equal to W, and that is codomain of f. And therefore f from W to W is 1. Now see here. Here f from W to W is an invertible function. Not here, therefore. An invertible function is f from W to W is 1, 1 and 1. Now see here. Now we want f inverse. If n is odd, then n minus 1 is even. And therefore, what is f of n minus 1? N minus 1 plus 1 is equal to n. And therefore, f inverse n is equal to n minus 1. If n is even, then n plus 1 is odd. And therefore, f of n plus 1 is equal to n plus 1 minus 1, that is n. And therefore, f inverse n is equal to n plus 1. And therefore, f inverse n is equal to n minus 1 when if n is odd. See, if n is odd, then this thing. N plus 1 if n is even. What is this thing? Is nothing but f of n. And therefore, f inverse n is equal to f of n. For all w belongs to, for all n belongs to w. For all n belongs to w. And therefore, f inverse is equal to f here. Clear? Next, before next, I would like to revise this thing. See here. See. N minus 1 is odd and n plus 1 if n is even. W is set of whole number is invertible. So for this one, what we need to see that 1 1-ness and 1 2-ness, then invertible. Clear? See, and that thing you already seen. For 1 1-ness, there are 3 possibilities. Both are even, both are odd, one of even, one of odd. Then find range. So 1 2-ness. Then find the inverse thing. See, n is odd, then n minus 1 is even. So if n minus 1 is equal to this one. Same way, if n is even, then this thing. In this way we can prove that thing. Let us see next one. Very simple sum. So here f is from R to R. Implies f of f is also from R to R. And therefore, for all x belongs to R, f of at x is equal to f of x is equal to what is f of x square minus 3x plus 2. Now what is f of something? F of something means here in place of x, x square, and in place 3 of x. So that is equal to sum square minus 3 times sum plus 2. What is that something? X square minus 3x plus 2, x square minus 3x plus 2. On simplification, you get the answer. Next. Here function f is from where to where? F is from R to open interval minus 1 to 1. And defined by fx is equal to x over 1 plus mod x is 1 1 and 1 2. That we want to prove. See, if we show given function is 1 1 and 1 2, definitely invertible function, and definitely the inverse exists also. Here I am also going to find a inverse also. Now see, here modulus is there. So there are 2 possibilities, x greater than or equal to 0 and x less than 0. Now first one, for x1 greater than or equal to 0, x2 greater than or equal to 0, f of x1 is equal to f of x2. This implies x1 over 1 plus mod x1, x2 over 1 plus mod x2, implies x1 over 1 plus x1, x2 over 1 plus x2. Why? Because x1 and x2 both are positive. So this implies cross multiplication x1 plus x1 x2 is equal to x2 plus x2 x1. Here x1. So x1 x2 get cancelled on both sides. What we get? x1 x2. What we get here? x2 x1. Clear? First one. Second possibility, for x1 less than 0 and x2 less than 0, f of x1 is equal to f of x2, implies x1 over 1 plus mod x1, x2 over 1 plus mod x2. This implies x1 over 1 minus x1, x2 over 1 minus x2. This implies x1 minus x1 x2 is equal to x2 minus x1 x2. x1 x2 get cancelled. What we get? x1 is equal to x2. Clear? Now third possibility is also there. One of them is non-negative, another one is negative. Third one, how to check it? If x1 greater than or equal to 0 and x2 less than 0, then definitely x1 not equal to x2. Yes. Also, f of x1 is equal to x1 over 1 plus x mod x1 is equal to x1 upon 1 plus x1. Why? Because x1 negative. Sorry, not negative. F of x2 is equal to x2 over 1 plus mod x2. And that is x2 over 1 minus x2. Clear? So, these and these both are unequal, and therefore f of x1 not equal to f of x2. Because see, x is always positive, here we get positive number. x2 is negative. x2 is negative. So here we get negative as well as positive, but some of them here positive, but here we get negative number. So they are not equal. Clear? And therefore, what we seen? For all x1, x2 belongs to R, x1 not equal to x2 in all cases. F of x1 not equal to f of x2. And therefore, f from R2 minus 1 to 1 is 1, 1. Now, how to check on-to-ness? Here. Suppose for every y belongs to minus 1 to 1, we have x belongs to R such that f of x is equal to y. Clear? There are once again two possibilities. X is greater than or equal to 0. If x is greater than or equal to 0, then what happens? If greater than or equal to 0, then f of x is equal to y implies x over 1 plus mod x is equal to y imply the x over 1 plus x is equal to y, imply the x is equal to x plus xy. Take xy on left hand side, same time take x common, so here y not x. What we get? Y. So x comes out y over 1 minus y. Y is not equal to 1, see, because we are taking in this that to that. If x is less than 0, then f of x is equal to y imply, yes what? X over 1 plus mod x is equal to y. So x over 1 minus x is equal to y. X is equal to y minus xy. X common 1 plus y is equal to y. Taking on left hand side, same time taking x common. So x is equal to y over 1 plus y. So in both the case there exists this thing. And therefore range of f is equal to minus 1 to 1. Or fx is equal to y, so that f is onto function. And therefore f from R2 minus 1 to 1 is onto function. And therefore, see, we want to see up to this state for a given sum. Whatever maybe here I am going to write, that is the extra part. And therefore f from R minus 1 to 1 is an invertible function S. F from R2 minus 1 to 1 is 1 1 and onto. And therefore what is F inverse? F inverse x is equal to, there are two possibilities. X over 1 minus x here. If x is greater than or equal to 0. X over 1 plus x whenever x less than 0. So in this example also inverse exists. Next one. Now see. Hey. See, starting of exercise 1.2. We've already seen x, x square, x cube, likewise. Injective means oneness. So that this one. That means start with f of x1 is equal to f of x2 and prove that x1 is equal to x2. Very easy to prove it from R to R. So I am leaving for you. So this example is for homework. Next one. Now see. See. Give examples of functions m from n to z, g from z to z that GOF is injective but g is not injective. GOF is 1 1 but g is not 1. Clear? Now see. Here f from n to z, suppose that f of x is equal to just x, and g from z to z, g of x is equal to mod x. Now see, GOF is injective but g is not injective. Please see here. Here g of minus 1 is equal to magnitude of minus 1 is equal to 1, and g of 1 is equal to magnitude of 1 is equal to 1, and therefore minus 1 not equal to 1, even though g of minus 1 is equal to g of 1, and therefore g from z to z is not 1 or injective. Now see GOF. Now GOF is function from where to where? Domain of f. What is domain of f? N to codomain of g. G of f of x is equal to g of f of x is equal to g of x only, because f of x is equal to x, and that is equal to mod x, and therefore gop at x is equal to mod x. Now see here, for x1 x2 belongs to n, because domain of f is n, gop at x1 is equal to gop at x2 is nothing but mod x1 barabar equal to mod x2. Please see here x1 is equal to x2. Why? x1 x2 belongs to n, and therefore gop is 1 1 or injective. See, hint is given here in our textbook, but in board exam they are not going to give hint. So remember these two forms whenever this particular sum is there, and this sum is a typical sum. Here, next one is also typical. Let us see. See here, on same way, one-to-ness is given. See, gop is 1 2, but f is not 1 2. Now see, f from where to where? N to n. Now, for f from n to n, f of x is equal to x plus 1, and g from n to n, g of x is equal to, let us consider x minus 1, if x greater than 1, 1, if x is equal to 1. Now see here, range of f is equal to n plus 1, n belongs to n, is nothing but n minus 1, and is not equal to n. See, is not equal to n, and therefore f is not 1 2. Now f and g both are from n to n, and therefore gop is also from n to n. Here f is from n to n and g is also from n to n, therefore gop is from n to n, and we want to show that that is 1 2 function. Now what is gop at x? Now for all x belongs to n, that is equal to g of f of x. What is f of x? Is x plus 1 is equal to x plus 1 minus 1, if x plus 1 greater than 1, is equal to 1, if x plus 1 equal to 1, is nothing but, what is this set? That is equal to x, such that x greater than 0, x belongs to n union 1, when x is equal to 0. That is not the case. Is nothing but n belongs to n, and that is equal to n, and that is equal to codomain of n, and therefore gop is 1 2. So remember this sum, this one, clear? Next one, now see here. Now dear friends, see here. Given non-empty set X, consider P of X is the set of all subset of X. Define a relation R in P of X. See, up to starting number sum 1 to 8, in which there are some based on functions are there. Now see, this sum is based on relation. See, P of x is nothing but set of power set of x. Clear? What is relation? Let us recall these things. For a non-empty set A, any subset of A cross A is called relation. Clear? Now, if x are x for all x belongs to A, or every order pair belongs to A cross A or in R, then that relation is called reflexive relation. Second thing, if xy belongs to R implies yx belongs to R, means x or y implies y or x, then such relation is symmetric relation. Third one, if x or y and y or z implies x or z, or xy belongs to R and yz belongs to R implies xz belongs to R, then that relation is transitive relation. Clear? Same way here. See, if relation is reflexive, symmetric and transitive, then that relation is equivalence relation. A number of sum based on that thing we already seen. Here, one more relation is also there. If x or y and y or x implies x is equal to y, if they satisfy this condition, then that relation is skew symmetric relation. See here, this relation is skew symmetric because A are B and B are A implies A is equal to B, because A equal to B, because A or B implies A subset of B and B or C implies B is subset of A. If A and B both are subset of each other, then it is skew symmetric. So here this relation is skew symmetric, and that thing we already discussed in starting phase of this chapter. We already seen this example also, but even though I would like to recall here. Now see, here for all A comma B belongs to P of X, A or B if and only if A is subset of B. Now see, first one, for all A belongs to P of A is subset of A. This implies for all A belongs to P of X, A are A, and therefore A are A. And therefore R is reflexive. Now it is not symmetric. For example, for if I take x is equal to 1, 2, 3, A is equal to 1, B is equal to 1, 2, implies A is subset of B, implies A or B, but B is not subset of A, implies B is not related with A. and therefore is not symmetric, and therefore R is not symmetric. Clear? Now same way, for all A, B, C belongs to P of X, let us consider A R B and B are C. Implies A is subset of B and B is subset of C. Implies A is subset of C. And this implies A R C. So this relation is transitive relation. Therefore R is transitive. R is not equivalence relation. Why? Is not symmetric. Because we know that a relation is an equivalence relation if and only if it is reflexive, symmetric and transitive. Clear? And therefore R is not equivalence relation, as it is not symmetric relation. Clear? Let us see next one. See here. Now it comes in terms of binary operation. See, for non-empty set, here A star B is equal to A intersection B for all AB belongs to P of X. It's a binary operation, but we can prove it also. How? Let us see. For all AB belongs to P of X, A intersection B is also in P of X. And therefore, for all AB belongs to P of X, A star B belongs to P of X. And therefore, star is a binary operation. Of course, here it is given, but if they can prove that it's binary operation, then we can prove it in this way also. This binary operation is commutative as well as associative. So I am leaving these two parts for you. Of course, here it is extra part, but do this thing. Next, so that X is the identity element of operation. Now please see here. Here, for all A belongs to P of X, we have X belongs to P of X such that A intersection X is equal to A is equal to X intersection A. And therefore, A star X is equal to A is equal to X star A for all A belongs to P of X. So this is the identity, because we know that for all A belongs to A, there exists E belongs to A such that A star E is equal to A is equal to E star A, then E is called identity. So here, and therefore X belongs to P of X is identity element. Only for X belongs to P of X, X intersection is equal to X is equal to X intersection A. No any other set is there. So for which intersection is equal to X. Only for X belongs to X. That is, only for X belongs to P of X, X star X is equal to identity is equal to X star X. And therefore X inverse is equal to X. See, X is only invertible element in P of X with respect to this binary operation star. Friends, here we can see that I am leaving this sum for you for union. A star B is equal to A intersection B is given to us. A star B is equal to A union B. A union B, then null set is the identity element. Sorry, null set is the identity element. And you can find inverse also, but only in place of the, that means same sum is not there. Identity is null set is identity element of for operation of this kind, and also find inverse of those set for which inverse element exists. So for A star B, that thing I am going to leave for you. Dear friends, this is the main exercise. Now only one lecture remaining to see this exercise. Few typical examples are there. That thing we are going to see in next lecture. And see, this completes the chapter 1. Please do all these sums, all illustrations are given, as well as solve all the assignments. Today I am going to post one more assignment for you. Please do that thing. Clear? Next time only one lecture remaining. After that one we are going to start chapter number 2. Inverse trigonometric function. Dear friends, one more thing is for homework to all of you is there. Please recall all standard forms of trigonometric function. We already listed all the standard forms whenever we are seeing that chapters. So recall all standard forms trigonometric functions, that is useful in inverse trigonometric form. Thank you, friends.